Okay, so what we're going to do now is we're going to talk about how we can identify certain aspects of a function by looking at its graph. So this section is mainly going to be visual. It's going to deal with a lot of graphing. Now, obviously, there will be some algebra involved as well. So the goal here is to describe characteristics of functions through their graphs. Okay, so with that said, what we're going to do is we're first going to start off with talking about the domain and range. So then the question becomes, well, how do we describe the domain and range visually? So the domain and range from a graph so basically that's what we're going to be doing. So we're going to say, look, the domain and the range are described as the x values and the y values the graph takes on. In interval notation. So I also want to point out that you're going to be basically stating the domain and range in interval notation, as we will be doing that a lot from this point on, and this is going to be common notation in calculus as well. So let's look at our first example. We're going to say find the domain and range of each graph. So to find the domain and range of each graph, let me first give you the graph. So this is -3, that's 2, so starts down here, goes up, and goes down forever. And then for part B, it looks like where this is a y value of 1 and -1. Okay, so let's start off with the first one. So the domain of this, if you think about it, is the x and y values. So in other words, when I move left and right, what values, what x values does this graph cover? So notice as I move to the left, this graph doesn't go past -3. In fact, since this is an open point, it'll never even get to -3. So, and then when I move to the right, what do I notice? This graph eventually moves to the down and right forever, which I don't care about the down part because the domain is left and right. So notice how this starts at -3, it doesn't include -3, and it goes all the way towards, it goes forever to the right. So the domain of this graph is -3, parentheses, because -3 is not included, to infinity. Now, for the range, as far as the up and down goes, the question is, how far up does this go and how far down does it go? Well, we know that it starts from this y value, whatever it is. We really don't care about that. You'll see why. See, this goes all the way up to 2, and then it stops at 2, and then it goes down forever. So the range of values that this takes on, or the largest y value it takes on, is 2, and the smallest, it actually goes down -infinity, so it goes down forever. So the range of this would be where? We always write interval notation from the smallest number all the way to the highest number. So it's from -infinity to 2, and we're going to put a bracket because in this case 2 is included. So if I were you, I would try to pause the video and try to find the domain and range of this before you press play, just so you kind of have some practice of your own. So to find the domain of this, what do we notice? This graph goes to the left forever because this arrow is suggesting it does. Where over here, notice how that point kind of stopped it, and it moves to the right forever. So what do you notice here? The domain of this is all real numbers, right? Because it goes forever to the left and forever to the right. So this is just going to be from negative infinity to infinity. Now, as far as the range is concerned, what do we notice? As far as up and down goes, we notice that the trend that this graph covers, even though these arrows are, I'm just saying it, this pattern continues on forever, the highest it'll go is up to 1, the lowest it'll go is to negative 1. So my range, remember, always from the smallest number to the largest number, is from negative 1 to 1, including negative 1 and 1. Okay, so now we're going to go on to solving equations and inequalities graphing. So we're going to say, look, solving equations and inequalities graphically. Okay, so now that we're going to be doing this, let's kind of talk about how we're going to approach this. So we would say the solution or solutions, because we may have more than one, of the equation f of x equals to g of x are the values of x where the graphs of f and g intersect. Okay, so when we're asked, hey, where does f of x equal to g of x, and we're asked to solve for it, we care about just the x values where the two functions intersect each other. Okay, so with that said, let's go on to the inequalities. Okay, so let's now say, well, what happens if we have, so then we'd say the solutions of the inequality f of x is less than g of x are the values of x where the graph of g is above the graph of f. So once again, what we're doing here is we're saying, look, where is f of x less than g of x? Once again, we're going to give the values of x, and usually this is going to be in interval notation. Okay, so what is it that I care about? Find out where g is greater than f, and that's what we want. Now what would happen, now I'm not going to rewrite this in terms of the other way, but I think it's self-explanatory. What if the inequality instead of less than was switched over to greater than? What would that mean? Then I would care for when f is above g, or vice versa. We could look at it as g is below f, right? So that's kind of what we're looking at. So we just need to graph our functions. Now for homework, some of the functions are simple enough where you can graph yourself, and there's others where there will be a graphing calculator symbol next to it, which would mean you could use a graphing utility to answer this question. So let's look at our second example, and we're going to say the following. Solve the given equation and inequality graphically. So we have for part A, we know that it's going to be x cubed plus 5x equals to 6x squared. Okay, so To graph these guys, the first thing I'm going to do is to find out where they equal. I first need to find out where they intersect each other, right? So if I were to graph these, and I'm going to graph them off to the side because we're going to need them in all parts A, B, and C. So x cubed plus 5x looks something along the lines of this. It's a cubic graph, so it does have its characteristics. So it kind of does this, and it does that, and it goes up. Okay? So then the x squared graph looks something like this, or the 6x squared graph. So this one is x cubed plus 5x graph, and then now I'm going to graph the 6x squared because I want to find out where these guys intersect, and it looks like this. So this one is the 6x squared. And if you look at it, these guys intersect in how many places? They actually intersect in 3 places. One is that, I think this one's obvious, x equals 0. The other one is here, which we got to figure out where they intersect, where that is, and then the other one is here. So the way I'm going to find these x values, I don't need a graphing calculator for this because all I really am doing is solving this. So to find those x values of those points, I could just literally use algebra to solve this. And see, if you think back to last year and I gave you this equation and I said, hey, solve this, what would you do? You would probably solve by factoring because you see the x cubed, the x's, and the 6x squared. So to solve this by factoring, we need to take everything to one side. So if I subtract 6x squared from both sides, I get x cubed minus 6x squared plus 5x equals to 0. So now I start factoring. Right away I see that they have an x in common. I factor out the x. I get x squared minus 6x plus 5. And then I see that this is a quadratic, so I could solve that by factoring further. And what does that factor to? X minus 5, x minus 1 equals 0. And we could see where the 3x value, and notice how I'm getting 3x values as the graph suggested. So the first one is where x equals 0. The second one is at x equals 5. The third one is x equals 1. So those are my solutions. That's the x equals 0. That's 1. That's 5. Okay? So my solutions are just these 3. Okay? And so we graphed them, we saw them, and I kind of did this algebraically, but technically speaking, we're supposed to look at the graph and give our answer. So it's 0, 1, and 5. Okay? Now, for part B, we're going to say x cubed plus 5x is less than or equal to 6x squared. Okay, so now what are we saying here? We're saying, now that we have this graph, actually, we can easily answer this question by looking at the graph. So we want to know, when is x cubed plus 5x less than or equal to 6x squared? So the equal to, remember, those are the places where they intersect. So in other words, when is x cubed plus 5x below or the same as 6x squared? So if I come back to this, what do I notice here? This is the graph of x cubed plus 5x. So x cubed plus 5x is below 6x squared where? All the way from like here, right? From negative infinity to 0. And then from 0 to 1, it's actually above, so I don't want that. So my answer is going to be what? So far it's going to be from negative infinity to 0, including 0, because at 0 it's equal to. Then I'm going to union that, right, because there's more than one interval. From 0 to 1, I notice that x cubed is actually above the x squared. But then it's below from where? From 1 to 5. And then after that, from 5 and on, it's above it. So my answer is going to be union from where? 1 to 5. Once again, I'm including the endpoints at 1 and 5 because at 1 and 5 it's also equal to. Now if this was just less than, then those wouldn't be included. It would just be parentheses. Okay? Now for part C, the answer is, the question is x cubed plus 5x is greater than 6x squared. So now what do I care about? I care about when this guy is above 6x squared, right? Because greater than. And I no longer want equal to, so the places where they intersect, it's not included. So if I come back up here, when is this above? It's above, when is x cubed plus 5x above 6x squared? Between 0 and 1. So I'm going to say, look, 0 and 1. Notice how I'm not including 0 and 1 because that's where it's equal to. And then from coming back up here, from 1 to 5 it's below, but from 5 to infinity, from here on out, from 5 and on, x cubed plus 5x is above 6x squared. So it'll be from where? From 5 to infinity, and these are both parentheses. Okay, so there's an example of where we solved equations with inequalities and equations as well. Okay, so now let's talk about defining where a function is increasing or decreasing. So definition of increasing and decreasing functions. So how do we know if a function is increasing? We'd say f is increasing on an interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 in that interval. So let's see what this is saying, because this is the definition of how we know something is increasing. See, if a function is increasing going from left to right, what should it do? It should go upwards, right? So what am I saying? If x sub 2 is greater than x sub 1, which what does that mean? If my x value at x sub 2 is to the right of x sub 1, then my y value at x sub 2 should be greater than the y value at x sub 1. So here's what this is saying. If this is x sub 1, this is x sub 2, notice how x sub 2 is to the right of x sub 1, which is that, then what am I saying? If from left to right this function is increasing, then clearly the y value at x sub 2 should be higher than the y value at x sub 1, and that's what this is saying. So that would mean it's increasing from left to right, it's going up, right? So hopefully this notation makes sense to you. If it doesn't, please ask and I'll clarify again, but this picture should hopefully clarify any questions you had about that. So then we would say f is decreasing on an interval I if f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2 in that interval. So this is now just going the other way, right? So if it's decreasing, it's going down from left to right. So the y value on the left side should be less, or on the right side should be less than the y value on the left side. So it's kind of doing the other way around. Okay, so once again, the key word is I've underlined intervals. So whenever you ask you to tell me when a function is increasing or decreasing, you have to use interval notation. Okay, so before we do an example where we'll talk about intervals of increasing and decreasing, let's also talk about local maxima and minima of a function, because we can then do one example that takes care of everything. So the local maxima and minima of a function. So we would say the first one, let's talk about the maximum. The function value f of a is a local maximum value of f if f of a is greater than or equal to f of x when x is near a. In this case, we say that f has a local maximum at x equals a. So let me kind of clarify what this is saying. See, this is saying, look, if I go to a value a, or an x value a, and I stay near a, right, because the key word here is what? Local maximum. So local means stay close. So if the y values, or if I take any x, so if I'm looking at the small interval here, And for all the y, for any x value I pick, if the y value is less than a, then what does that mean? A is a local maximum, which means kind of like when we have like this hump right here, right? Kind of like that. That creates our local maximum. Now, if you're ever asked to tell me where the local maximum is, we always define it with the x value. So just keep that in mind. If I say, hey guys, where are my local maximas? You always say, hey, my local maximum is at x equals a. Now, if I say, hey, what's my local maximum value, then I want the y value. So f of a is the local maximum value. X equals a is the location of my local maximum. Are we all clear with that? Because that gets a little tricky. If I say, hey, what's the local maximum value? You'd have to give me the y value. If I say, tell me, state where the local maximums and minimums are, then you tell me with their x values. Okay? So for the local minimum, it's literally the same thing. It's just now we're saying, hey, all the y values at a, or the y value at a is the smallest, locally, once again. The keyword is local. So the function value f of a is a local minimum value of f if f of a is less than or equal to f of x when x is near a. In this case, we say that f has a local minimum at x equals a. Okay, so once again, the minimum value is f of a. The location or the place of the local minimum occurs at the x value. So for example 3, which this will be our last example, we'll kind of put everything together. State the intervals in which the function is increasing or decreasing, and also state its local maximums and minimums. Okay, so we're basically doing one example that takes care of the two concepts we talked about earlier. So, and to be honest with you, this stuff hopefully is not difficult because we're basically just viewing the graph and answering what's happening. Okay. And it stops here. Okay, so when it's decreasing, and this is a y value, x value of 2, so here's the graph, so it looks like this. So to find out where it's decreasing, when I go left to right, it's when the graph is going down. So look, starting from -7, and this is kind of like a point, it starts from here. From -7 to -4, it's decreasing. So now, whether you choose to include -7 or -4, it doesn't matter. You could use either parentheses or brackets. Either way, it's fine. As long as we know that it's decreasing from where? From -7 to -4. Now, from -4 to 2, it's increasing, so I don't care about that. We're only talking about decreasing. And then, but what do I notice? I'm going to union it from 2 and forever, 2 to infinity, it's going downwards. So it'll be from 2 to infinity. Okay, so that's where it's decreasing. Where is it increasing? Well, where is it going up and down, or upwards from left to right? So we said this was decreasing, and what do I notice? From -4 to 2, it's increasing, and that's the only place it's increasing. So The interval where it's increasing is from -4 to 2. Now remember, these are strictly just the x values. We always describe intervals of increase and decrease in terms of x. Okay, now how about local minimums? Do we have a local minimum? Do you find the place where it kind of goes down and then it starts increasing, which actually we have a local minimum where? At -4, because what is it doing? It's going down, and it stops, it's going up, which creates the minimum. So we have a local minimum at x equals -4. Now remember, we're talking about locally. We're not saying this is the lowest it'll ever go, but if I kind of focus on the graph just in this region, what do you notice? This is the lowest value it takes on in that neighborhood, right? Locally, that's the key word. Now, how about local maximum? Do we have a local maximum? We actually do. Where is it? It's at, it goes up, then goes down at x equals 2. Okay, so we identified pretty much our local min, our local max, and we have our intervals of increase and decrease. And those are, now if I say, hey, what are the local minimum values and the local maximum values, then you'd need the y values. But this is just saying, hey, tell me where the local mins and maxes are, which is just through the x values. Okay, so that takes care of section 2.3. As always, don't hesitate to reach out if you have any questions.